All right, so continuing on from hydrogenation, let's look at a halogenation problem. So write the bromination reaction of cyclohexene. So you notice it doesn't say that it's a halogenation reaction, but I recognize bromine as a halogen, so I know I'm talking about a bromination reaction or halogenation reaction. Okay, so to start with, I'm going to draw my formula for cyclohexene. So one thing you'll get probably pretty good at in this class is drawing hexagons if you weren't already. So one of my methods for drawing hexagons is to, I draw my two lines and then I kind of put a dot above and below and then I connect, and that kind of gets me a hexagon. If I try to just go and draw it, they tend to be a little bit more circlish. This one's questionable too. Now I have a cyclo, so I did make sure it was cyclic. I have hex, which is 6, so I knew I was making a hexagon, and then I have ene, so I know I need a double bond in there. Where do I put the double bond? There's no number. Well, it doesn't matter since there's only one single double bond here. Every single one of these carbons is equivalent. So you and your partner might draw completely different cyclohexenes, but they are actually the same thing because each of these carbons is an equivalent position. So I'm going to put my double bond right there for simplicity. And one of the things with our line formulas that you have to get kind of used to is that idea of do remember the implied hydrogens. So like here I have 2 implied hydrogens. I'm going to put them there just to kind of remind my brain. But here along the double bond I only have 1 because this carbon can only have 4 bonds, and 2 of them are taken up with the double bond and 1 is with this other carbon, so there's only room for 1 hydrogen left. So I'm going to have the bromination reaction. So I'm going to react it with bromine. Bromine is diatomic, just like our hydrogen was, and just like all the other halogens would be. So make sure you get that 2, that subscript 2 there. And then one of the differences between the halogenation of an alkene and the halogenation of an alkane is that this one occurs readily. It does not typically, especially with bromine, does not require any type of catalyst. So no light needs to be written here, no heat, nothing like that. It's going to happen readily. So what is my product going to be? Well, think about what's going to happen. You have this very reactive double bond here, and we're going to have that opening up, the little drawbridge, and we've got these 2 jazz hands. So we're going to add, remember our bromine could be thought of this way, we're going to add a bromine across the double bonds. They can't both be added to the same carbon because there isn't really enough room. Even if this carbon loses the double bond, there isn't enough room for 5 things bonded to it. So they have to add across. That's what we say, across the double bond. One added to one, one added to the other. And so what I end up with is a brominated cyclohexane. So it's, which I would name 1,2-dibromo cyclohexane. So I've saturated it, so I've lost the double bond, and I've added, there's still that implied hydrogen there, and I don't need to worry about any type of catalyst here. And because this is symmetrical, we're adding bromine, each carbon got the same thing, so it's symmetrical. We don't have to worry about who gets what because it doesn't matter if this one goes here and this one goes there. We create the exact same structure. So let's look at one where we do have to take that into account. And that would be our first example of a unsymmetrical addition, which is hydration. So write the hydration reaction of propene. So for this one, I'm going to go ahead and do structural formulas. So I'm going to do, there's my 3 carbons. So prop means 3, and then ene means a double bond. And again, I could have triple bonds here. We don't worry about hydration of alkynes in this class, but for the other ones, we could be talking about alkynes. I just find it simpler to start here. Where is my double bond going to go? It doesn't matter because putting it between carbon 1 and 2 is actually the same as putting it between carbon 2 and 3 because the molecule could be flipped. So that's why there's no number needed on propene. So then when I go to put in my hydrogens, I need to make sure that I put in the correct number. So for example, this carbon here already has 3 of its bonds used up. So I only want to give it 1 hydrogen. And this carbon has 2, so I want to give it 2. So notice the different number of hydrogens that each of my carbons ends up with. So write the hydration. So if someone tells you, they're not hydrating enough, or, what do they need to drink? They need to drink water. So this is the addition of a water molecule. right? So plus water plus H2O yields. Hydration reactions do require a little kick in the pants, and this is a really common catalyst that you're going to see, which is it requires a little bit of an acidic catalyst. You're going to see that a lot in a lot of the different reactions. So you can do that by writing like H plus there. Sometimes you'll see it just as listing a specific strong acid, such as sulfuric acid. Either of those are fine. They convey essentially the same thing. If you move on in chemistry, you will learn about exactly why this is needed and what this proton does and why it allows this reaction to happen. We don't get into electron mechanisms in this class, but essentially it gives the carbon a little kick in the pants to make things a little bit more attractive for different parts of the water and so on and so forth. So how does this reaction happen? Let's, instead of thinking of water as H2O, let's think of it this way, because that's going to help us mentally translate into what's going to happen here when that double bond opens up and, you know, drawbridge, jazz hands, etc. So if we're going to lose this double bond, I'm going to put a little like kind of a dashed thing so I can see, okay, I've got these two spots now, because if the double bond goes away, this carbon would only have 3 bonds, so we could bond another thing. And one of them is going to get the hydrogen, and the other is going to get what we call a hydroxyl group, so the OH from the water. So together this is our water, but as far as how it's going to get added across the double bond, we're going to add the OH so that you can see how it's unsymmetrical. These are not the same, therefore this is unsymmetrical addition, right? So let's say that this hydrogen gets added here. So we're going to get, okay, carbon and carbon and carbon, and I'm going to get all my hydrogens. My pen's having a little trouble with my hydrogens here. You can see why line formulas can be really nice. Saves you time. So I'll try to draw this one. This is my new hydrogen. So it got added here. I'm going to circle it so I can keep an eye on it. And then the other one, here, our OH group right there. Now we haven't learned about this organic family yet, but you'll recognize we'll learn about it in the future. We've actually made an alcohol. This is an OH. It's a little hard to tell. Sorry about that. So that we've opened up across the double bond, added across. Now, the problem here is because it is unsymmetrical, we could have also made something different. We could have made a different isomer could have been generated, because this hydroxyl group could have gone here to the first carbon instead. Could have gone there, and this carbon of the double bond could have gotten the hydrogen instead. You know, fill in the rest with hydrogens as needed. So I'm going to leave the hydrogens off. Don't do that on your test or quiz, but just so we can focus on that. So this is where Markovnikov's rule comes in play for our unsymmetrical addition reactions. So we have to consider both of these are actually going to get made. I mean, that's really the thing. If you had a little flask and you're doing this reaction, both of them would get made. The question is, what's the major product? That's not how you spell that. Lordy. The major product versus the minor product, meaning what one is going to happen the most often. So let's say like 9 out of 10 times, which one is going to be made. And Markovnikov's rule, you know, is about like, oh, the one with the most alkyl groups and blah, blah, blah. I like to remember Markovnikov's rule this way. This is what works for my silly little brain. Silly little memory tips help me so much. I like this little expression. The rich get richer. Now, that's not the actual translation of Markovnikov's rule, but it helps me, and I think of hydrogens kind of like little money symbols, you know? Like, you know, they got the little H almost there. And so what that tells me is that the carbon that already had the most hydrogens is going to be the carbon that more often than not gets another hydrogen. So in terms of who gets the hydrogen, who gets the hydroxyl group, if the rich get richer, carbon 1, remember how I said they have different number of carbons, carbon 1 here had, let's count them, 1, 2 hydrogens, and carbon 2 only had 1. Therefore, this one, where the carbon with the most hydrogens is going to be more likely to get created than this other one. Now, that doesn't mean it doesn't get created, but it is the major product. So maybe if I could isolate my products, I'd find out that 80% of them or something are this, and only 20 are that, or 90 and 10. So this happens more. Nature seems to prefer this. The rich get richer. Nature prefers in this unsymmetrical addition that the carbon with the most hydrogens is the one that gets the new hydrogen when the double bond opens up and grabs onto the hydrogen more often. And we see that again in our hydrohalogenation. So if we react hydrogen chloride with ethene, so ethene would be nice and simple, 2 carbons. Eth means 2 carbons, and then ene means there's a double bond, and hydro, and then chlorine is a halogen. So that's why it's a hydrohalogenation reaction. So I'm going to add across the double bond, and one of them is going to get a hydrogen, and the other is going to get a chlorine. Now you'll notice here that it actually wouldn't matter where I put which, because they would both end up, rather than being different isomers of each other, they're actually the same molecule, because I could just turn it around. So even though this is technically unsymmetrical addition, where we'd want to consider Markovnikov's rule, in this case it doesn't matter. They both have the exact same number of hydrogens, and both products that potentially would be created are the exact same thing rather than different isomers. So in that case, I end up with a saturated alkyl halide. It doesn't matter where I put them, because now we have free rotation around the single bond. So, and they're all equivalent. So now I would have, chloroethane instead of the original ethene. So I want to talk just really briefly about addition polymers of alkenes, and there's more detail in another video for you, or in another lecture. So some things to know is you probably are familiar with polymers, but just in case, poly means many. And so polymers are really big molecules, macromolecules that are composed of repeating subunits. So something repeats over and over, or there's a pattern of this one and this one and this one and this one. But I always think of this toy we had growing up. We had a lot of babies in our household growing up, and you could pop these, they were like ginormous baby beads into each other to build this long chain. And that's what polymers are like. And so you're probably familiar with polymers if you've ever taken biology, because our carbohydrates and our proteins and our nucleic acids are all polymers. They're long, big molecules made up of these repeating subunits. Mono means one, so are monomers. So addition polymers are repeated, building from an original alkene. Now, they're not actually alkenes anymore in the polymer sense, in the polymer state, but they started from an alkene monomer. And they too are just addition reactions. So here is our monomer. So this is some generic one. The R just means like rest of molecule. Maybe those are hydrogens, maybe there's something else, but you can see we have a double bond here. So this double bond could open up. We have the 2 carbons still single bonded together, and we have the 2 jazz hands that could grab onto something. Well, what they could grab onto is another one of these that also opened up. And you can do that over and over and over. And there are a lot of things you're probably very familiar with, like PVC pipe, or most plastics, like polyethylene, that are addition polymers of alkenes, adding across the double bond, except what we're adding in this case is another alkene that also opened up and is now grabbing onto the other carbons. And you'll learn more and get some practice on those in another lecture. So let me know if you have questions or concerns about these Furious 5 addition reactions of our unsaturated aliphatic hydrocarbons.